A thread lighter than breath catches stones on the wind. Strength hides in a molecule folded like origami while the air holds its line. This is a spider, turning liquid protein into a wire thinner than dust. Inside silk glands, soluble dope flows through narrowing ducts that impose shear and align chains. As pH and ions shift, beta sheet crystals lock while amorphous regions stay elastic. The spinnerets pull and twist, tuning diameter, water content, and final toughness on demand. Dragline silk forms lifelines, frames, and safety cables, strong for weight and forgiving under shock. Other glands spin capture threads, egg cases, and wrapping bands with very different rheology. Function splits across organs. Each nozzle evolved to solve a precise mechanical and chemical job. Glue droplets along capture silk, manage humidity, spreading, and detachment to hold better, then release. The Darwin bark spider throws anchor lines across rivers, suspending giant orbs over open water. Such spans demand fibers that resist creep, tolerate gusts, and survive wet nights without collapse. Ballooning spiders cast threads skyward and ride convective currents for kilometers over fields and seas. Electrostatic forces and light winds lift them when lines reach nanoscale diameters and low mass. Travel demands toughness against sudden pulls, yet elasticity to buffer oscillations without tearing attachments. Web-building strategy arranges radial spokes and sticky spirals so impacts spread through multiple pathways. Hubs and guy lines distribute loads, preventing local failure and letting repairs stay small and quick. Spider silk properties change across the web, matching tasks from sensing to capture to scaffolding. What governs spider silk strength may follow several routes working together. Possibility 1. Protein motifs tune crystal size. Possibility 2. Shear and draw align chains tightly. Possibility 3. Salts and pH control water removal that locks amorphous regions for elasticity. Engineers chased these principles for sutures, parachutes, and silent deployable structures in small drones. Wet adhesives mimic silk glue droplets, balancing humidity response with peel strength and clean release. Scaled spinning lines adjust solvent, ions, and draw rate to approach nature's tunable composite. Is spider silk stronger than steel appears often, but context matters beyond headlines. Per weight, toughness and elasticity excel. Absolute breaking loads depend on diameter and weave. Webs win by dissipating energy, not by matching cables one-to-one in raw force. Silk also carries information. Vibrations map prey, size, direction, and struggle through radial lines. Damping and tension are tuned during the night, like a musician retuning between songs. When rain threatens, some spiders dismantle sections to avoid sagging loads and wasted repairs. A single animal turns chemistry, mechanics, and behavior into a modular, renewable infrastructure. Different glands assign roles, spinning conditions tune edges, strategy stitches pieces into resilient architecture. Performance emerges from cooperation, not a single miracle material. Spider's silk, nature's superfiber, threads physics into wind like a quiet bridge between leaves.